Let's dive into the world of differential equations. These are mathematical equations that describe how quantities change over time. Think of it as a way to model how things evolve, whether it's the population of a city, the temperature of a room, or the speed of a car. At its heart, a differential equation is a statement about rates of change. For example, dy divided by dx equals the rate of change. Before we dive deeper, let's establish some mathematical ground rules. First, the derivative notation. You'll often see dy divided by dx, which represents the rate of change of y with respect to x. It tells us how much y changes for a tiny change in x. Another common notation is f prime of x, which signifies the derivative of the function f at a specific point x. These notations are fundamental for modeling dynamic systems, meaning systems that change over time. Let's look at a classic example, the population growth model. This model describes how a population grows over time. The equation dp divided by dt equals k times p represents exponential growth, where dp divided by dt is the rate of population growth, p is the population size, and k is a constant representing the growth rate. The solution to this equation is p of t equals p naught times e to the power of kt, where p of t is the population at time t, p naught is the initial population, e is the base of the natural logarithm, and k is the growth constant. This model has numerous applications, including bacterial colonies, population dynamics, investment growth, and even cell division. A key concept here is that the growth rate is directly proportional to the current population. Let's see how we can implement the population growth model in Python. First, we import the NumPy library as np. Then we define a function called exponential_growth that takes three arguments p0, k, and t, representing the initial population, growth rate, and time respectively. The function returns the population at time t using the formula p0 times imp@exp of k times t. We can then use this function to calculate the population at different times. For example, if we start with a population of 100 with bacteria doubling every hour, we can use this function to calculate the population after 5 hours. Now let's consider decay processes, which are the opposite of growth. These models describe how quantities decrease over time. The equation dn divided by dt equals negative lambda n represents exponential decay, where dn divided by dt is the rate of decay, n is the quantity, and lambda is a constant representing the decay rate. The solution to this equation is n of t equals n naught times e to the power of negative lambda t, where n of t is the quantity at time t, n naught is the initial quantity, e is the base of the natural logarithm, and lambda is the decay constant. Examples of decay processes include radioactive decay, drug elimination from the body, cooling processes, and capacitor discharge. The key concept here is that the decay rate is proportional to the remaining quantity. Let's look at a code example of radioactive decay. Again, we import the NumPy library as np. We define a function called radioactive_decay that takes three arguments, n0, half_life, and t, representing the initial quantity, half-life, and time respectively. We calculate the decay constant lambda_val using the formula np.log of 2 divided by half_life. Then we apply the decay formula to calculate the remaining quantity at time t, which is n0 times np.exp of negative lambda_val times t. For example, we can use this function to calculate the remaining amount of carbon-14 after 11,460 years, given that its half-life is 5,730 years. Next, let's discuss simple harmonic motion, which describes oscillatory systems like a pendulum swinging back and forth. The equation d squared x divided by dt squared equals negative omega squared x represents simple harmonic motion, where d squared x divided by dt squared is the acceleration, x is the displacement, and omega is the angular frequency. The solution to this equation is x of t equals a time sine of omega t plus phi, where x of t is the displacement at time t, a is the amplitude, omega is the angular frequency, t is the time, and phi is the phase constant. Examples of simple harmonic motion include a pendulum swing, spring oscillations, sound waves, and AC electrical circuits. The key concept here is that the restoring force is proportional to the displacement. Let's visualize simple harmonic motion using a sine wave. We can represent the motion with the equation x of t equals a times sine of omega t plus phi, where a is the amplitude, omega is the angular frequency, and phi is the phase. The amplitude, denoted as a, represents the maximum displacement from the equilibrium position. The frequency, denoted as omega, represents the angular frequency of the oscillation. The phase, denoted as phi, represents the initial phase shift of the wave. Differential equations have a wide range of real-world applications. In biology, they are used to model population dynamics, enzyme kinetics, epidemic spread, predator-prey cycles, and cell growth rates. In physics, they are used to model heat transfer, radioactive decay, damped oscillations, circuit analysis, and wave propagation. In economics, they are used to model market growth, interest calculations, supply-demand models, investment returns, and economic cycles. These are just a few examples of how differential equations help us understand and predict phenomena in various fields. In summary, we have explored several key differential equations. The growth equation, dp divided by dt equals kp, describes exponential increase where the rate is proportional to the current value. The decay equation, dn divided by dt equals negative lambda n, describes exponential decrease where the rate is proportional to the remaining quantity. The oscillation equation, d squared x divided by dt squared equals negative omega squared x, describes periodic motion created by a restoring force, resulting in sine waves. These equations demonstrate how real-world phenomena can be modeled through rate equations. In conclusion, differential equations serve as a bridge between mathematics and the natural world, allowing us to understand and predict change. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.